Is the screen visible now? The new screen? Okay, we have seen these fundamental operations. Okay, now let's see a type of signal called even odd signal. So what is a even signal here? So we have seen the flipped in the previous one. Yeah. So we'll focus on this operation here. So what happens here is it just becomes a mirror image of it. So this reflects on this and you get a signal like this when you do a flip. So basically you're flipping the signal in X. So what happens here is, one second, yeah. So what am I saying here is this is the definition of even signal, that is flipped version of the signal is equal to the signal flipped in X basically. So this is even signal. So how can we represent this? We can represent x of t, x of minus t, when you flip the signal, will be equal to the signal x of t. So this is a even signal. So for example, let's take a signal of this sort. Let's take a sinusoid itself, a cosine, or let's take this half raised cosine part of the cosine curve, and you see that whenever I flip this, if I do a flip of this, what happens? It remains a similar one because it is symmetric around the y-axis. This is y-axis, and you see a nice symmetry across y-axis. Therefore, whether you flip or you keep the signal same, it is same. So this type of signal is an even signal. And there is also a signal called odd signal. Is my slide changing? Yeah. So here what is this? Signal flipped, that is x of minus t, is negative of the signal. So this is the odd signal. So can anyone give an example of odd signal, or if you can explain me how to draw, I can draw on the screen. Okay. So what is an odd signal here? Mirror wave. Maulika, what do you mean by mirror wave? Yes, correct. 1 by x. Yes, right. 1 by x is also that. So I'll just give a simpler example. If you take a one cycle of sine curve like this, yes, the cosine is even signal, sine is the odd signal. This is a sine, one cycle of sine, and this is one cycle of cosine. So in this case, if you flip the signal, it will be this way, and this is nothing but same as flipping in y also. When you flip along y-axis, you'll get a similar curve like this. So this is a type of odd signal, and this is a type of even signal. Is everyone here with me with even and odd signals? Okay. So basically one principle is any signal can be split into even part and odd part. Basically x of t plus x of minus t by 2 will be the even part of the signal, and x of t minus x of minus t by 2. This will be any signal x of t can be split into, let's denote it by xo of t, and this by x e of t. So this is another principle that will be useful later, that any signal can be split into its odd or even parts, or if you add odd and even parts, you get back the signal x of t. Is this part clear, this one? Okay. So basically, if you add x even of t, this part, and x odd of t, this results in the signal x of t. Fine. Okay, cool. So now there is another type of signal. I think slide changing is taking a bit of time. Do you all see a slide change, or is it on the same slide?
It's the same slide.
Is it? Okay, yeah. Wait. It's taking some time. Arey. Oh my. Okay, so did it change completely? No, wait. Something is weird. Give me a moment, I will reshare the screen. Oh yeah, now it came back. Yeah, fine. So the other type of signal here is called periodic signals. So we have dealt with periodic signals before, like sinusoid and cosine curve, sine curve, the complex exponential, etc. But we will revisit, because there are any signal that repeats itself periodically is called a periodic signal. How do we represent a periodic signal? So now, using the operations that we have discussed, like the shift operation, what does this mean is, if a signal x of t, if I shift this by a period, a certain period capital T here, it will be equal to the signal, it will be same as a signal, and it will be same even if I shift in multiples of capital T. Here n is the multiples, that n can take all integers, n belongs to integer, that means n can take values 1, 2, 3, so on so forth. So this is a basic definition of a periodic signal. Any periodic signal, if you shift it, it will again be the same signal. So for example, let's take a signal x of t here, and how does a periodic signal of this looks like? If you have at every, okay, the drawing is not to scale, but yeah, if you get the point. So basically, even if I like I'm here, let's say I'm here, and shift by t, I'll be here again. It repeats the same values anywhere you take and as a reference and shift it by t, it repeats itself. So this is called a periodic signal. Is everyone clear with this periodic signal? Because this is important for understanding Fourier series later. Great. So now we understood periodic signals, but some signals are very standard signals. These are called canonical periodic signals or standard periodic signals. So it what I mean by standard, it acts like a base for representing any signal. So this will be more clear as I discuss Fourier series. But what are the two types of standard or canonical periodic signals? One is sinusoid, as you see here. So this is a sinusoid signal represented by cos, but it's a sinusoid signal. It can either be cos or sine. So what are other parameters here? This represents the amplitude, this represents the frequency, this is as time progresses, the time axis basically, and this represents the phase. So generally phase is 0, you get a exact cosine curve like this. Okay, and if the phase is shifted, if there is a phi shift here, let's say, you'll get a signal like this. Okay, it will be shifted a bit. Okay, so in this signal, it is periodic and the time period is 2 pi by omega naught. Basically, if you remember equation of a cosine or cosine function when you're doing your mathematics, so we see that whenever you shift by 2 pi cycles, it is again the same signal. This cosine will be repeated again. So basically here t will be 2 pi by omega naught. Omega naught is the frequency of the signal, which is also represented as 2 pi f if f is in hertz, and here it is in radians per second. So you can also see that the time period is inversely proportional to the frequency of the curve. Here you can write t is also equal to 1 by f, right? If you replace omega naught by 2 pi f. So this is one of the standard periodic signal. So are the components of sinusoid clear here, and what is meant by canonical? Okay. So there is another type of periodic signal called complex exponential. This is called complex exponential. So even we can't represent in a one-dimensional signal like the cosine here. In the last class, we have shown on a circular space a rotating, a rotating stick around a unit circle, right? So that can be represented by e power j omega naught. But even this is periodic with the same period as what we saw in the standard sinusoid function. So here also t is 2 pi by omega naught, and we'll see later why we are using this as another canonical periodic signal. So basically it makes Fourier series analysis very compact, so it becomes easier to see the signals or spectrum, etc., with this kind of a complex exponential. So these are the two standard periodic signals. So any doubts here of okay, so basically if I replace t by 2 pi omega naught, what you'll get is e power j omega naught t plus omega naught n 2 pi by omega naught. So if I cancel these two, it will be nothing but e power j omega naught t plus 2 pi n. So if I shift a sinusoid by 2 pi or any multiples of 2 pi, it's the same thing. So basically here the t 2 pi by omega naught justifies that this is a periodic signal, and similarly for the cosine here. So because we have read that e power j omega naught t can be represented as cos omega naught t plus j sine omega naught t. So these are basically a complex representation of cosine and sine curve. So based on this, obviously they'll have a similar period, right? Okay, so this is about periodic signals. We'll keep it aside for a moment. We'll come back to it when we deal with Fourier series. Uh, so yesterday it wasn't very clear, like why is e power j theta cos theta plus j sin theta. So I will just clarify a little bit so that it will become more intuitive for you and it will be more comfortable. So here j is nothing but a square root of minus 1. So for now you just remember at the face value that it is just this as a fact. And so is anyone here aware of how we can write exponential as this? So e power theta can be written as this series. It's called series representation of an exponent. Is anyone aware or any idea of how we get this? Okay. Okay, so basically to clarify others who are not aware of this, so it comes from the Taylor's series notation. So how do we represent? So what happens is any smooth function, let's say one second. Sorry. So any smooth function can be approximated as a sum of series. So around a given point, let's say a point of interest is x naught. So what we do here is we can write this as f of x naught plus f dash of x naught. Sorry, one second. Yeah, it can be represented, yes. So x minus x naught plus by 2 factorial. I hope people are aware of this notation, but I will explain if possible. So what this apostrophe means is it's nothing but a first differentiation of the function f of x at point x naught. So it is nothing but d f of x by dx at x naught. Similarly, the 2 apostrophes implies it's a second differential, d square f of x by dx square at x naught. So is everyone aware of this notation, the apostrophe on a function? So even if you are not aware of it, it's fine. Just remember at the face value that it's a differentiation of a function. What is differentiation? If you have a curve, you can find the slope of it, right? So let's say there is a curve like this. At this point of interest, I can find what is the slope of this. So basically we are approximating a smooth function with slopes at different values, and that is represented by this. This is called the Taylor series. Now one second. Yeah, so if you apply this Taylor series for exponent of this sort, this is a f of x here for us right now. F of x is nothing but a power x, and about the point 0, if I do a Taylor series expansion, it gives me of this sort, that is f of 0, which is nothing but 1 here, and so on and so forth. So if you know differentiation of a power x d, so it will give you a power x log to the base c times a. So this is a differentiation of x. Like that you can differentiate multiple times and you can expand into this expression. And now if you replace this a by e, which is a natural exponent, so if you replace a by a real number e here, a can be any real number. Now we are putting a number called e here. So when you expand that way, it will result in, yes, yeah, it will result in this kind of a notation. Now we can replace sorry, yeah, now we can replace e power theta with j theta, so which results in, like, wherever theta is there, you can put a j theta here. Let me put here. So you can put j theta square, so on, so forth. So then you will get 1 plus j theta plus, sorry, it will be minus theta square plus minus theta cube, so on, so forth. You see what happens here is there are a mixture of real terms and a complex terms. Complex terms in the sense whichever is accompanied by j, this way. So this will also have j, so on, so forth. Now if you separate out the real and imaginary parts here, you get all the even powers, yeah, so on. And similarly, these are the real terms, and the other terms which have imaginary part, j theta minus j theta cube plus j theta power 5, okay, so on. So this is called imaginary terms. These are imaginary terms. So when you can basically have real terms and imaginary terms. When you separate it out, this will be nothing but okay, I'll write this side. So this is nothing but sorry, so this is cos expansion. Similar to Taylor series, you can expand cos theta and sin theta, and this is sin theta's expansion. So this way we can represent a complex exponential as cos theta plus j sin theta. So these are all the real terms, these are all the imaginary terms, and if you take j as common factor, you get only the theta in the sin theta term. So is this clear, the proof of why e power j theta is cos theta plus j sin theta? Okay, is everyone with me here? Okay, great. So now there is also a geometric perspective that you can see. So as shown in the last class, let's represent this as this is imaginary axis and this is real axis, and you can also call it as x-axis and y-axis. So a Cartesian plane can be represented using complex numbers here. So that is another idea which gives a geometric representation of this. So let's say a vector is there in space xy axis, and the orientation is a theta here, right? I think there is some delay, but yeah. So now if you project this vector onto x-axis, this becomes cos theta, and if you project onto y-axis, it becomes sin theta. And you can represent this point as let's say right now the vector length is 1, okay, cos theta comma sin theta. Also you can put show it as one number as cos theta plus j sin theta. So this is another representation showing the geometric representation of a point with this complex exponential, which is also equal to e power j theta. So If theta is 0, let's draw another one. If theta is 0, it's just on the x-axis, and as you increase theta, it starts rotating, right? And when does it come here? When it is pi by 2, right? So that will be minus I. So this will be 1 plus I. If you multiply, so basically sorry, yeah. So basically, if you multiply any number by j, it will shift the vector to the y-axis. So this is another interpretation of multiplying a number with the complex number j here, which is the under root of minus 1. So is this part clear? So e power j is 0 we started with, and we started, if you add pi by 2, it becomes this. E power j pi by 2 is nothing but equal to j, because cos pi by 2 plus j sin pi by 2. So this will reduce to 0, and this will reduce to 1, and you are left with j. So
Here's what I found.
oh, yeah. What is this? Wait. Yeah. So let's say you have a number here, let's say some 10. If I want 10j, where will it be? It will be on the y-axis. Basically, it is rotating this 10j. So basically, this is also called a rotation operation. Whenever you multiply with j, it rotates. So basically, this e power j theta has a capability of rotating on a two-dimensional plane. So that is what we were seeing in the last class. So is this representation clear for the Euler's representation, the geometric representation? Okay, fine. So okay. So we'll discuss a bit about compact representation of sinusoids. So let's say we have a sinusoid like this. So I'm using here the sine and cosine interchangeably because after all they are sinusoids. So we have this a sine omega t plus phi, which is a sinusoid with omega has the frequency, a as the amplitude, and theta phi as the phase. Okay, any sinusoid of this sort can be represented by sine and cosine. How is it possible? We'll see that. So we are seeing at this can be split into some a1 times sine omega t plus a2 times cos omega t. So so basically this thing is called in phase component. So for we are starting with sine, and this is also sine, so you can say that these are in phase components. And there is another orthogonal component, that is cos, because sine and cos are always orthogonal, and we call this a quadrature component. So any general sinusoid of this sort can be represented by sine and cosine, and one part is called in phase component, the other part is called quadrature component. So how are we getting this? So if you remember from your high school trigonometry, there is this identity called sin c plus d. So if you can recall, and here it is here even. So basically what you're doing here is this c will be omega t and d will be the phi. Now if you split this, it will be like, let's, so this will be, this is corresponding to c, this is corresponding to d. So sin c will be omega t and cos phi, and similarly cos omega t and sin phi. Now there is also amplitude, but for now we'll make a has 1. So this cos phi is a constant value depending on what is the phase offset of the sinusoid. So now this can be represented as a1 sin omega t plus a2 cos omega t. Is everyone with me here on this slide? Okay, great. So so any general sinusoid can be represented with in phase and quadrature component. And so now we'll shift to Fourier series. So until now what we learned will be useful, and it will help us in understanding the Fourier series or its derivation. So we have seen a periodic signal being represented by this, right? T plus nt, and t is the time period, that is where it repeats itself, and it can repeat in any multiples of capital T here. So now what is the concept here is any periodic signal can be represented as sum of standard periodic signals. What are the standard periodic signals? As we discussed, these are the sinusoids. So basically this thing, the title of the slide, we are representing in terms of equation as any periodic signal x of t can be represented as sum of sines and cosines. So why not only sines? Because we have seen just now that any general sinusoid can be split into in phase and quadrature component, and therefore this, like for every n, this is one signal. So like that you're adding multiple standard cosines or sines, and you get this representation. So yeah, so this is basically called Fourier series. So we'll see why it is of this sort, but here the concept is for different n's you have different periods, right? So so any periodic signal can be represented as sum of canonical periodic signals at different harmonics here. So you can increase n in 1, 2 and so on. Okay, so yeah, and for now you remember that how to find this coefficients, the an and bn. So an is nothing but 2 by t signal times the particular cosine that you are the an is coefficient for, and you find the area under that multiplied curve between the time period in one time period, and similarly for bn. So this will give the coefficients of this, and this is the Fourier series equation here. So yeah, so if you want the intuition, it is nothing but a periodic signal is being represented in terms of other periodic signals, which are cosine and sinusoids here. So if it is already periodic signal, you can also use another periodic signal to represent the same signal. So that's the idea here, and this is one of the compact equation for representing a periodic signal, and it's called Fourier series. So any periodic signal can be represented this way, right? So this is simplest form, but it looks complex because it has many terms. It has a naught, a n, b n, sine, cos, etc. So this is called a trigonometric Fourier series, and the subscript here represents nothing but x of t is periodic with period t, similar to what we started with. And this is the, so if we take the denominator 2 into the coefficient itself, we can represent it as another coefficient, but I have written it as a naught here. So this is what a Fourier series representation is, and the coefficients are computed by this as shown here, 1 and 2, this 2. Okay. uh, since I told it can be represented by a sum of canonical periodic signals, so we also saw that the complex exponential, that is e power j n omega naught t, is also a, so basically how we are getting this n omega naught here is, if you replace t is equal to 2 pi by omega naught, you get uh, this from here. So from this representation to this n omega naught t. So this will be used interchangeably many times. T is equal to 2 pi by omega naught, which we can replace or we can use t. So yeah, and then there is a compact representation using Euler's equation. So why we are using this? It's a complex representation because we are compressing it everything, but it makes lot of calculation later very simple. So that's why it's called compact representation. So similarly, any periodic signal can be represented with this, right? So e power j and omega naught is a periodic signal, that's a standard canonical periodical signal, and Cn is the coefficient for that particular signal. So we can form a relation between these two by equating them. So this is x of t and this is also x of t as well. So now if you equate both the right hand sides here, this and this, you can find a relation between Cn and An and Bn. So the summary is, this is a more compact representation of Fourier series. It's called exponential Fourier series, where you use a complex exponential to represent the canonical periodic signal here, and any periodical signal can be written as a sum of this canonical periodic signals. So if you equate this and try to compare one by one at the same frequency what coefficient is, you will get some equations like this, where a naught and c naught, that is the first coefficient in exponential Fourier series, is equal to the first coefficient in trigonometric Fourier series, and you can look up into these equations. But more importantly, Cn can be represented of this way. Cn is nothing but the first the nth coefficient of accompanying cos minus the j times the coefficient accompanying sine here on that nth frequency. So basically here omega naught is usually called as first harmonic, 2 omega naught is called second harmonic. So these harmonics are more useful in music signals because even the notes in music are also harmonics here. So they're also very periodic signals with certain frequencies. Is everyone clear with this Fourier series notation, or why we go for this? If you have any doubts, please ask here. Okay, so okay, we'll do some demo here. Just give me a moment. Okay. Yeah. Okay, is the screen visible with the code? Can you see this code, everyone? Okay, cool. So here we are just visualizing some Fourier series here for few signals which are periodic. So what we are doing is we are just importing some libraries which are required for executing the code, and we have created few functions, few signals here, or sometimes signals and functions are interchangeable use. So if I say function, you just understand it's a signal, or either way. So what we are doing here is we are creating a sampling frequency and creating four functions, four periodic functions. This is called a lambda function, where you can compactly write a function to create a waveform of this sort, or anything. If you want to do as a compact function, you can use this lambda representation. So you don't have to worry about it now. I'll send a cheat sheet where you can map what are different functions of in Python, etc. So for now, just remember that using this lambda functions, we are generating this periodic signals. So the first one I will execute here. So the first plot you see here is a square wave. So you repeat the square wave periodically. So this is one wave, and the same thing is being repeated at every integer 1, 2, and so on so forth. For now we snipped it before the 2 here. So can anyone tell what type of signal is this? Is it odd or even signal? The first left corner plot here. Odd signal, right? Yes. So has two of the audience pointed, it is an odd signal. Why is it odd signal? Anyone wants to answer? My own.
It is not symmetric about the origin line.
Correct. Has Shavik pointed it out? So when you take a y-axis here, you see that it is not symmetric. It is the negative of it. So when you draw y here around 0 and here, you see it is antisymmetric. It's called antisymmetric, and if it is symmetric, it's an even function. So for example, an even function is this one. If you see this is very symmetric around 0. If you draw a y-axis at 0, you see it is symmetric around that y-axis point. So right. So these are some of the periodic. This is called square wave. This is called sawtooth. This is a complex one where we try to mix two triangle signals together, or sawtooths. And this is another signal where we use a x square as a signal, right? X power minus as a signal here. So these are the few periodic signals that we generated using this code. Okay. So yeah. Now we'll define a function which will calculate the Fourier series. So basically we are calculating Fourier series using these equations. If you remember correctly, we use an integral, that is finding the area after multiplying the signal with the cos. So that is exactly what we are doing here, and we will get the coefficients an and bn. So if it is not clear, I will again show you. So yeah, as you see here, these ones, you can see these, right? An and bn. So because it is implemented in a computer, we can't use a integral. So what we do is we use a summation in that whole period for all the samples present. So yeah. So this function is for finding the Fourier series coefficients. Okay. So yeah. So let's plot for one function here, that is the first function for a square wave. What could a Fourier series look like? So okay, ignore this one for a moment, but yeah. So as you see, right, uh, this square wave, you have this Fourier series coefficients a n and b n, and this is due to number precision. It goes to 10 power minus 16, but if I limit the axis, it is nothing but 0. All these are 0. So you see here that ans are 0 because can anyone tell why this is so small? These ones, these are actually 0. So I will tell why these are 0, but only bn's are present. So you see these are the coefficients of bn's, and they go to 0 alternatively. So one is very high, 0 keeps decaying, and alternatively goes to 0. So this is the Fourier series coefficients of the square wave signal here. So what does it tell is, uh, when I add a signal of this much amplitude at this frequency, the sinusoid at this frequency, and keep adding, I get the approximation of the square wave. So basically what we are doing is we are just representing this as sum of sines and cosines, and all the ans are 0 and only bns are finite, and this is the trend of what bns follow to represent this signal. So if you had this much amount, the let's say it's 1.3 amount of this sinusoid at 1, then sinusoid at n equal to 3, and so on so forth, you get this signal. So basically, any guess why these are zeros but these are finite? The ans are 0. I can show you the Fourier equation once again so that it will be more clear. So basically what we are seeing is the ans are 0 but bns are finite, and this is for this square wave. Any idea, any guess?
I wanted to ask one thing. I forgot it actually. So an was the coefficient of the sine part or the cos part?
Cos part.
Cos part. Okay.
Yeah.
So we can see that it's an odd signal similar to a sine function. So that is why we could understand in a sense that the dependency is on a sine function rather than on a cos function.
Correct. So exactly as Shavik pointed out, because it's an odd signal, cos is a even signal, but sine is an odd signal, and this is purely odd signal. So therefore the coefficients an becomes 0. It is shown here with like it looks like this because I didn't limit the axis, but if you limit the axis, it is close to 0. You can see 10 power minus 16 here. So yeah, as Shavik pointed, it is right. So now let's try to reconstruct based on this. So what we are doing here is, so we defined a reconstruct function where it uses this an and bn, takes the sum and plots it. So what we are plotting here is three things. So the blue one is the original curve here behind, which can't be seen, but which is behind. You can see a blue one here. So this is the original curve, and then we're summing up 20 harmonics. So we are taking n equal to 1 to 20 and summing all those cosines and sines. In the next orange curve, in the next green curve, we are taking 100 harmonics, that is n equal to 1 to 100. So if you're getting confused what is meant by n here, so here we are summing across n, right? So we can sum until infinite, but now what we are doing is we are taking n equal to 1 to max limit 20, that is the orange curve or the yellow one, and n is equal to 1 to 100 is the green one. So, so as we see, as you increase the number of harmonics in representing this square wave, you see the approximation becomes more and more close. So as you go on increasing the harmonics, the approximation becomes more and more square wave like. So it approximate this, and this can be similar thing can be done for other waves also, which I'll share this notebook. You can try on other other periodic signals as well, but I'll show a demo of I'll show a small gif of how multiple components adding shows approximation of this. So yeah, so we have seen this. So let me show this. Focus on this first. I'll share the laser pointer. Okay. So okay. Okay. So you can see here, these are all zero. ANs are zero as we discussed. But as the number of components increase, you see more and more approximation. It becomes more and more close to the square wave. So same thing what we plotted, we have just simulated it across multiple harmonics. So as we increase the, if you see the other this double sawtooth wave also, you see as they increase, as the harmonics increase, it approximates more and more. There are some end effects or edge effects. This is called Gibbs phenomenon, which usually happens because you can't go to infinity in a real case. Ideally we can, but not in real time, or when you're doing a real computer simulations or representing a signal in a computer, etc. So similarly, you see a sawtooth here has the, here also you see the AN is 0, but here you see AN is not 0, BN is 0. So because this is a even type of signal, therefore this is a purely even signal, therefore the odd components goes 0, that is the cos coefficients goes 0, sorry, sine coefficient goes 0, and cos coefficients are finite. And again when you see sawtooth, which is a odd signal, you see AN 0 and BNs are some finite values, and as you increase the number of harmonics, it approximates the signal well. So is everyone with me until this point? If everyone understood Fourier series and their representation? Okay, I see only one thumbs up. Okay. Okay. So hopefully this part is clear. I think we're running out of time. But yeah. Anyway. So if anyone of you have doubts until this point, let me know, because until this point is very important to understand the next part, the Fourier transform. So if the Fourier series part is clear, just give a thumbs up, or you can look into it again later when we upload the recorded videos also. So yeah, okay, cool. So now we have seen Fourier series, but that is how periodic signal can be expressed in terms of sum of sines and cosines, which are another periodic signals. But the question is, what happens to the signals which are aperiodic, which are not periodic? So and usually that's the case. Any physical signal apart from music is a periodic signal. Apart from instrumental music, any other thing is aperiodic in nature. So whether you take EEG signal or your speech signal, etc., those are all aperiodic in nature. Or sometimes they're quasi-periodic, which is not pseudo-periodic, which is not exactly periodic, but they have some structure of that sort. So the question here is, what about aperiodic signals? So how do we do that? So the trick to get the Fourier coefficients of aperiodic signal is nothing but you extend this. Let's say this is aperiodic signal, you just have this signal here, we try to extend it. So virtually we just add same signals at every t, at every t intervals. So that makes, we extend this to a periodic signal, we make it a periodic signal here with a period t. That means the same thing repeats every period t. Okay, so now what we do is, I'll just go a little fast here, but we can discuss again in the next class. uh, what happens here is, now we do a Fourier transform, Fourier series on this periodic signal, and then limit the t to infinity. So we start expanding this time period t to infinity, that becomes this signal again. So we split this into Fourier series, then limit the t to infinity. As t tends to infinity, what can happen to the series? So that results in a Fourier transform, and Fourier transform is what we use on any aperiodic signal or any signal, not just aperiodic. We can even use Fourier transform on periodic signals as well, uh, which is nothing but which results in a Fourier series itself. But yeah, so is this part clear? Intuitively, I haven't shown the equations, how we are doing this. Okay, maybe I can show. Okay, okay, fine. Okay, we have seen this. So basically, we are approximating x of t to x tilde of t, which is a periodic version of a aperiodic signal. This is a aperiodic signal. Okay, yeah. So now we are extending it to a periodic signal x tilde of t, which can be expressed as sum of, let's say, a k. K is just a subscript, k we are summing over k. K is 1 to infinity e power minus j, sorry, plus j n omega naught t, right? So this is a Fourier series. Here omega naught is nothing but 2 pi by t. So we can represent this as k is equal to 1 to infinity a k e power j n 2 pi t by t. So this is what we got from Fourier series. Okay, so now we want of the frequency content of this signal, right? So that means whatever Fourier series represents, this ak is the frequency content. So it says this harmonic is present at this level. So we want the coefficients ak, and we have seen the formula for that. Ak is equal to 1 by t integral in one period. The period here is extending from minus t by 2 to t by 2. So we go from minus t by 2 to t by 2, x tilde of t e power minus j 2 pi, or we can just put n omega naught t, that is easier way to t. So yes, and dt. So this is what we have seen previously, how the coefficients are represented. So now this we can take and represent t times ak is equal to integral minus t by 2 to t by 2 x tilde of t e power minus j n omega naught t dt. So is everyone clear until this point of how we got here from x tilde? Okay, great. So after getting this, what we do is we try to extend limit t tends to infinity, what can happen. So this is the expression that we got, right? If you see in the last end of the previous derivation. So yeah, so now let's limit t tends to infinity, what happens, we'll check. 1 by t becomes infinitesimal, but let's not touch it right now. So now as t tends to infinity, right, the uh, what happens here is there is nothing beyond this, right? As t tends to infinity, you see the whole thing expands. So you just get this one. So basically you can represent it as x of t. X tilde of t is nothing but x of t as t tends to infinity, and you can just integrate in the time period, that is t by minus t by 2 to t by 2, and e power j k omega naught t dt. Now what happens to k omega naught? So because omega naught is also dependent on capital T, and capital T is like the time period of the periodic signal we are extending to infinite, so that you will get the period is infinite. That means you have only the signal of interest present, that is the aperiodic signal. So let's take this omega naught is equal to 2 pi by t. You have 0. You have basically this is the omega axis, right? So you have k omega naught, that is 1 omega naught, 2 omega naught, so on so forth, which is nothing but oh, can you guys see the slides? Yes. So 2 pi by t, 4 pi by t, so on so forth. So now as t tends to infinity, what happens is these points come closely by, they come very close, so they become very continuous like this as t tends to infinity, because t is in the denominator. As t tends to infinity, this becomes more continuous. So when it becomes more continuous, we replace this k omega naught by omega, right? Omega is saying that it is more continuous, not a discrete value anymore as t tends to infinity. So you get 1 by t integral minus t by 2 to t by 2 x of t. Basically it is in the range of signal, the integral limits, e power minus j omega t dt is nothing but ak here, and t ak is represented by integral minus t by 2 to t by 2 x of t e power minus j omega naught t dt. So basically if you do this operation, you'll get a Fourier transform, and now ak is no more ak because k becomes more continuous, there is no discrete. So basically we replace this t ak by x of j omega, okay, which results in this Fourier transform minus t by 2 to t by 2 x of t e power minus j omega t dt. Did everyone understood what I did here? If anything is confusing, we can do it again later, but if you have any specific doubts, please ask here. Okay. So basically, what in summary, what we are doing is, for x of t, which is a aperiodic signal, we construct a periodic version of it by making multiple copies of the same signal uh, at every time period capital T. Okay. Then now this x tilde of t has a Fourier series, and now what we do is, as t tends to infinity, what happens to this Fourier series is nothing but Fourier transform. So now the main key takeaway is, any signal x of t can be transformed into its frequency components using a Fourier transform. If it is a periodic, you get a Fourier series. If it is a periodic, we call it a Fourier transform. And from Fourier series, we can derive a Fourier transform based on this, hack, by making a periodic signal periodic, then getting its Fourier series, then extending t to infinity. So that is one thing, and this is what it says. Any signal can be split into its omega, or you can write omega as 2 pi f also, frequency components. So you can, x of omega says at a given frequency or at a given omega, what is the like what is the power of that omega present in the signal x of t. Okay, this gives the frequency content of a signal, and it's called Fourier transform. So there is also inverse Fourier transform. We can see its derivation later, but you can just imagine, you can multiply both sides by e power j omega t, and you can get this form of inverse equation. So this also you can get just by taking Fourier series and doing the reverse way of representing x tilde of t. So from this we can derive. So how we can derive is, x tilde of t is nothing but summation of ak e power j n omega naught, or k omega naught, k omega naught t, right? And k is equal to, can go to minus infinity to minus infinity, doesn't make sense here. We go from k equal to 1 to infinity. Okay, so similar to what we did before, if we expand this, we can get a inverse Fourier transform also. And then what we do is, t tends to infinity, then omega naught tends to infinitesimal d omega, because it is nothing but 2 pi by t, which goes to very small value, which is represented by d omega. And since it becomes more continuous, we will replace it with an integral. So it will be like 1 by 2 pi. There will be 2 pi down, because this t ak is x of e, x power j k omega naught, e power j k omega naught t, right? And dt, and this goes to in that particular period, and this k omega naught tends to omega, this d omega, so this summation becomes an integral. So this way we can get inverse Fourier transform also. So basically the thing I want to say here is, Fourier transform is invertible. So once you do a Fourier transform, you can revert and get the signal back. So basically it is a reversible thing. So, and it represents the same information contained in a signal, but it makes it clear to visualize which frequencies are present to what extent in a given signal x of t. So is this clear until this point? Okay. So in this class we have just discussed about how to represent signal x of t in terms of Fourier series and Fourier transform, and what is the relation between Fourier series, Fourier transform, and what is the meaning of a Fourier transform basically. So it says about the frequency content in a signal. So if I get a particular coefficient in a Fourier series, I say that this harmonic is present in the signal to this extent. Okay, so similar way, when you extend it to a continuous aperiodic signal, it becomes the frequency content at that particular infinitesimal frequency. What is the power of the signal? So basically, when we say a signal spectrogram, it's nothing but we're just doing a Fourier transform and plotting this x of j omega naught j omega. Uh, so j omega t, that gives the spectrum of a signal. So there are I wanted to show a few signals where which are important, but I think we're out of time. So in next class we'll continue with this rectangular pulse uh, and sync functions, which are very important for understanding any signals or uh, so basically you have to remember this uh, things for specific signals like rectangle, impulse, and sinusoid signal. And we'll also deal with what is a Fourier transform of a periodic signal. So we will also see this in the next class, and then deal with estimating spectrum and see a example of real time signal and how the spectrum changes. So is it fine? I think I will end the class now because we have passed 10 minutes. So any doubts until this point, please let me know. So we'll deal with this rectangular pulse and all in the next class. So yeah, thank